Hello, in this video we will talk about weak acid strong base titrations and go from there. Alright, so a titration, just a reminder, it's an addition of some carefully measured volume of solution, and sometimes you know the concentration of one and not the other, or you know the identity of one and not the other, or in the case of what we'll talk about here, is you know the identity and concentration of both and you're trying to find something like the pH or the Ka or something like that. With an acid-base titration, it's a neutralization reaction. And when you have added enough base to neutralize the acid or vice versa, you reach the endpoint. Alright, here's the slide from the strong acid, strong base titration video, which talks about the possible problems we can ask you. And now these ones where you're trying to find concentration or molar mass, this is the same regardless of whether you have strong things or weak things, because all that matters is the moles and the molarity, and not so much whether it's strong or weak. Because if you're adding, say, a strong base to a weak acid, it will still force the reaction all the way to completion because it's a strong base, and it does what it wants to do, irrespective of the weak acid's desire to make an equilibrium. Alright, but when you're trying to find pH, now everything is different because we have to deal with the acid equilibrium, and that changes a whole bunch of things. And so that's what we'll talk about here. We're going to look at how to find the pH during the titration. And so our titration curve also looks different, right? The little dotted line down here is what it would look like if you had a strong acid. But now when you have a weak acid, which is this, your shape looks a little different because along the way it makes a buffer. So you start out with just the acid, and then you convert some of that acid to its conjugate base, and that makes a buffer. You can calculate the pH of this with the Henderson-Hasselbalch equation after you do the stoichiometry. And when you're halfway there, the pH equals the pKa for reasons that you'll see in a minute. Something else that's new here is the equivalence point is at a pH greater than 7. So its X value, down here would be the same, because that just depends on concentration. But the Y value is higher. The pH is greater than 7. And this is because you have just the conjugate base left at the equivalence point, and that functions like a base. The volumes are still the same, so that's not changed. So overall, when you're doing these titrations, you need to consider 3 different chemical reactions. So here's another drawing of the curve. And so you have your weak acid equilibrium equation. And so when you're just here at the start of the titration, you just have a weak acid, and that's described by this equation. As you proceed through the titration, adding the strong base will convert the acid to its conjugate base, and this is the equation involved for that neutralization reaction. Notice this is not equilibrium, it's a forward arrow because this reaction proceeds quantitatively, as we say in the biz, which means that it makes as many products as you put in reactants, given the limiting reactant. So before the equivalence point, the hydroxide is the limiting reactant, you'll have leftover acid. Then, with that leftover acid and the conjugate base you've made, then it sets up an equilibrium, and this is called a buffer. Now, at the equivalence point, all that's left is your conjugate base, this thing. Because you've reacted all of the acid and turned it into conjugate base, so now your acid and base have the same number of moles, assuming it's a 1-to-1 reaction, which it usually is, but not always. And then that conjugate base, since it's the conjugate base of a weak acid, it legitimately functions like a base, and it makes hydroxide. So notice that these 2 equations, while they're both equilibria, they are fundamentally different. Here the acid makes hydronium, here the base makes hydroxide. So it's not just the reverse, it's a completely different equation, because now you have much more weak base than you do its conjugate acid. So, alright, this makes the pH of the endpoint basic, and we'll talk about that in our calculation. After that point, now you're just adding the base to water. So however much base you add past the equivalence point, the hydroxide is in excess, and then it very quickly dominates the pH of the solution. And so the contribution to the pH from the conjugate base is very small compared to this hydroxide, so we can ignore it and just look at the hydroxide once we're past the equivalence point. Alright, here's another way to say the same thing. This is the same summary slide as we had in the strong acid, strong base video, but now it's the weak acid version. So before you add the strong base, you're just dealing with weak acid equilibrium, just like we've done before, not a surprise. When you're partway there, you first have to do the stoichiometric step of this strong base added to the weak acid, the forward arrow that makes its conjugate base, and then you can do a buffer calculation. If you use Henderson-Hasselbalch, the nice thing is that you can do this in moles, so you don't have to figure out concentrations, it saves you a step. When you're at the equivalence point, again, you still have to think about this stoichiometry, but it's pretty straightforward that however much of this you added, you have the same amount of this, and you've made entirely conjugate base. Here, you're going to do equilibrium, you need concentrations and not moles, and you've added more liquid to your solution, so you need to divide by the new total volume, and then you can do your hydrolysis. It gets you POH, and then you can convert that to pH. And then when you're past the equivalence point, you now have to do some stoichiometry to think about, all right, I added 120 mils of base, 100 of that was neutralized, so I got 20 mils left. That kind of stoichiometry, and how many moles does that relate to? You got to divide by the new total volume, and then your concentration of hydroxide gives you POH, which then you can convert to pH. Let's try it. So we're going to use acetic acid. Here's the equation for it, and we'll just use a bunch of ones. So 100 milliliters of 0.1 molar acetic acid is present originally in your container, and you're titrating it with 0.1 molar sodium hydroxide. All right, here's the Ka. A little different than the Ka that we've shown you for this before, because I pulled it from a different textbook and didn't feel like changing my slides. All right, and so here's the problem. You're going to calculate the pH after you add the following volumes of sodium hydroxide. Whoa, this is a problem. How do we start? The way that I always start this is I try to figure out which one of these represents the equivalence point, or another way to say it as which type of calculation do you have to do for each part. All right, it's pretty obvious that this, you haven't added any base yet, so it's just a weak acid calculation. Let's see here. Okay, now I got to figure stuff out. For this problem, since there's equal concentrations, that means that equal volumes of this will reach the equivalence point. So that means this one down here is our equivalence point. Okay, from that you can figure everything else out. Here's the equivalence point. At C, you're halfway to the equivalence point. B, you're in a buffer region. And E, you're past the equivalence point. So I highly recommend doing this step first to figure out what the heck you need to do, because depending on where you are in the titration, you have to do very fundamentally different calculations. Another thing is, if you think you're at the equivalence point and you start doing the math based on that and it goes weird, maybe just double check that you're actually at the equivalence point. All right, so step 1, we haven't added any hydroxide yet. So we're here on the titration curve. And so this is just a weak acid problem. By now this seems simple compared to everything else we've done, but at one point this was hard, right? So we have a weak acid. We assume that we start with just the amount of weak acid and no hydronium or conjugate base. This thing's shifting to the right. The equilibrium here is defined as Ka for this particular reaction. Great, we solve for x. For this problem, we can neglect x, and x is just 0.1% of what it's subtracted from, so that's a great thing to neglect x. Now, it's always good to see what the heck x is equal to. All right, x is equal to the concentration of H3O+. Perfect. So then I can take the negative log of that, and that gives me the pH. And since there's 3 sig figs in the number inside the logarithm, that means we have 3 decimal places. All right. Next, let's calculate the pH in the buffer region. We've added 40 milliliters of sodium hydroxide. So we're in the buffer region. We're not quite halfway to the equivalence point. So let's do the buffer problem. Now, the first step is we have to figure out how much of each component we have. So this is the stoichiometry. We start with pure acid when we do the titration, and then we've added sodium hydroxide, which converts this acid to its conjugate base. And for this reaction, it turns out that the number of moles of conjugate base is equal to the number of moles of strong base that we added. So how much hydroxide did we add? Well, here's the concentration, moles over liters. Here's the volume of it that we've added so far. That means there's that many moles of hydroxide. And since it's a 1-to-1 stoichiometry, this means that that's how many moles of conjugate base that we have formed. Okay, so we're also going to want to know the number of moles of acid that we started with. So here's moles over liters times liters, and that gets us the number of moles of acid. So we start with 0.01 mole of acid, and then we react away 0.004 moles of it. So that means we have 0.006 moles of acid left, and then we've made 0.004 moles of this conjugate base. So now we can do the Henderson-Hasselbalch equation, and we can do this just in moles, and this is super handy because we don't need to convert to concentrations. If you do convert it to concentrations, to say do a normal icebox, just keep in mind that your total volume is increased. So now instead of 100 mils, you have 140 mils. So you have to account for that dilution. But if you do it in moles, you don't have to worry about it. Just throw the moles in here, and then you'll get the pH. All right. So now let's carry on. So here we are halfway to the equivalence point in the middle of the buffer region. And so here pH equals pKa. There's a good discussion of this in your textbook, but hey, the pKa is 4.754, so that's the pH. The reason why is because when you're halfway to the equivalence point, you have half your original acid left, and then you've converted half of it to conjugate base. So then this is the log of 1, because these cancel out, so it's the log of 1. The log of 1 is equal to 0, so your pH equals your pKa. And so that's why. All right, still moving. Now we're at the equivalence point when we've added 100 milliliters of sodium hydroxide. So this is a pH of a salt problem because the sodium hydroxide turned all of the acid into conjugate base. And then the only other ion in solution is the sodium, which is the conjugate acid of a strong base and therefore doesn't hydrolyze water, and we don't have to worry about it. So we effectively just have the acetate here. We're going to use an icebox with now the base equation, right? Here's the base. It makes hydroxide. It happens to be the conjugate base of our weak acid, which is fine, but this is going to do base things. Now, we also need to know the new concentration of the base. Iceboxes and equilibria all depend on concentration, so we need to know what that is. So we're going to need moles over liters. We got to find the moles first. We have a couple different ways we can do this. You can say, all right, I added 100 milliliters of sodium hydroxide. I know the concentration of that. Or you could say, I know the concentration of acid that I started with, and then that all converted to conjugate base. Either one works. It gives you the same numbers. So here's the number of moles. Then you divide by liters. Again, your total volume has increased. So now we have 200 milliliters total. So we have to account for that dilution. And then once we do that, we can then plug this number back into our icebox and solve. One more step. We need the Kb for this because this is a base equation. So we need to use base. Kb for base. All right, so you take Kw over Ka. It gives you Kb. We've done this before. So now you have Kb. It's equal to x squared divided by the equilibrium line on the left. You can neglect x here, and it gives you this value. And so now, what does x equal? X is equal to HA. Well, I don't really care about that. Oh, it's equal to the concentration of hydroxide. There we go. So now if you take the negative log of this, you get POH. And then you subtract that from 14, and you get pH of 8.73. All right, last step. Let's calculate the pH after we add 120 milliliters of sodium hydroxide. So now we're past the equivalence point. And so this is a pH of a strong base problem with one little thing on the front end. You have to figure out how much base you added after the equivalence point. So you can do this in terms of volumes. You can do this in terms of moles. Either one's okay. I'm going to do it in volumes here because I just find that easier. So we used 100 milliliters of the base to reach the equivalence point. So that means the sodium hydroxide from this first 100 milliliters was all reacted and turned into something else. But since then, we've added 20 milliliters additionally of sodium hydroxide because total volume we've added minus the amount that was neutralized gives us how much is in excess. So now this 20 milliliters of sodium hydroxide, we can use that to find moles. 20 milliliters, here's the concentration of the sodium hydroxide solution. So here's the number of moles of hydroxide that you've added in excess. But this concentration is what's in your burette up top. Down in the solution below, well, it gets diluted. And so you have to account for that new total volume, and it gives you this concentration. I mean, you could use M1V1, M2V2 for this as well. M1, V1, you're solving for M2. The sum here is V2. that would work just as well. And now that you have the concentration of hydroxide, you can use it to find POH, subtract it from 14, and then you get pH of 11.96. And now we're done. So overall, you know how to do all of these pieces separately, or at least you should by now know how to do all of these pieces separately. We're just putting them all together into one big giant problem. So try to keep that in mind. First you have to find where you are in this whole thing, and then from there, know what you have to do in order to get your answer. But then the pieces there you should be able to do. It's just the hard part is putting them all together. One last tip. Please only use Henderson-Hasselbalch equation in the buffer region. I see people use it up here. I see people use it down here. I think I've seen somebody use it way up here. No, right? This is only in the buffer region. Another interesting thought is the Henderson-Hasselbalch equation doesn't work very well on the little shoulders here of the buffer region, because in these points, you're kind of transitioning between a buffer and this place where the conjugate base starts to determine the pH. And so it's not a discrete transition. It kind of slowly merges from one to the next. And so in this middle region, we don't really have a simple equation to describe what's going on. And you'll see this in your laboratory experiment. You do this, and if you use this math to try to calculate pKa, you get at least a value in here that makes some sense. Out here, the value starts getting weird. And down here, the value is weird too, because you're transitioning between just a weak acid to this buffer. And the assumptions you make with Henderson-Hasselbalch don't hold down here. So keep that in mind. In the ballpark of this flat spot is where you can use the Henderson-Hasselbalch equation and have it make sense. Another thing is the base and acid in here refer to the weak acid and its conjugate base. So this is not sodium hydroxide. I see people do that all the time. Don't do that. It's the conjugate base. Oftentimes, the moles of conjugate base are the same as the moles of base that you added, but you always have to think about that first. And that's all I have. Thanks for watching.